This is Part 4 of Lecture 2b for ECE 361, Probability for Engineers, Fall 2016, Drexel University. In Part 3 of this lecture, we covered Section 2.1 and introduced some basic concepts from random variables. Now, in this fourth and final part of this lecture, we'll go over the notion of probability mass functions and introduce four fundamentally important discrete random variables: the Bernoulli, the binomial, the geometric, and the Poisson. Let x, the capital letter X, be a discrete random variable. In general, I'll try and use capital letters for random variables near the end of the alphabet. That is, S, T, U, V, W, X, Y, and Z, written as capital letters, will typically denote random variables. Our canonical random variable will be called x. Let this symbol, which is script x, be the set of values that the random variable x can take. We call x, script x rather, the support. Formally, x is the range or image of the function x. Recall that x, the random variable, is technically a function that maps the set of outcomes, omega, to the real numbers. Consequently, the support, script x, are all numbers x in the reals for which there exists some outcome in the set of outcomes that maps from omega to little x under that function. Said again, script x, the support, is the range of the function x. It's the set of values for which there exists at least one outcome omega that maps to that number x. The probability mass function is for the case of discrete random variables, is a vector that's defined on the support. Script x is a probability vector. It's denoted in bold as a bold p. Sometimes we'll write p sub x to emphasize it is the probability mass function for the random variable x. This vector p has elements p of x, one such element for each value x in the support. Said it alternately, this vector p, the probability mass function for the random variable x, is a vector whose elements p of x, one for each x in the support, is said to be a valid probability mass function if it satisfies the following two properties. First, the probability that the random variable takes each possible value x must be non-negative. This follows from our axiom 1 of probability. Secondly, if I add up the probabilities that the random variable takes each value x in the support script x, I should get 1. This is simply a consequence of the normalization axiom of probability. Looked at a different way, any vector p satisfying the above two properties is a probability vector for a random variable on that support. Let's do an example. We toss a fair coin twice, and we let the random variable x be the number of heads. So the support of that random variable is 0, 1, or 2. And we're mapping the outcomes, heads and tails, tails and heads, tails and tails, and heads and heads. Those four outcomes are mapped to the three values 0, 1, or 2. In particular, if I get tails, tails, there are no heads, and therefore x equals 0. If I get tails, heads, or heads, tails, there is one head, and therefore the random variable takes value 1. Finally, if I get heads, heads, there are of course two heads, and so the random variable takes number 2. I add up the probabilities of all outcomes associated with a given value of x, and that's the probability that x takes that value. since there's only one outcome tied to the event that the random variable x takes value 0, namely tails, tails, the probability of that event is 1/4. Since there are two outcomes, each probability 1/4, tied to the event that the random variable x takes value 1, I add those up, I get a half. So, recall their shorthand notation. P of x means the probability of the event that the random variable x takes value little x. And again, this is the probability that the outcome of the random experiment is such that the random variable x maps that outcome to the value little x. In other words, we can view the random variable x as a function that partitions omega, the set of all possible outcomes, into events which we'll call E sub x, one for each possible x in the support. In particular, E sub x are all outcomes omega such that the random variable x takes the same value x. For example, if I consider x equal to 1, then E sub 1 are all outcomes that map to 1. In particular, in this case, the outcomes being tails heads and heads tails. Here we see formalized what we did intuitively in this example. The probability that the random variable x takes value little x is the probability of the event E sub x, and by the discrete probability law, that's the sum over all outcomes in that event of the probability of that outcome. Recall that E sub x, viewed as a collection, one for each x in the support, is a partition of omega. As with all partitions, if I take two values, x and y, that are distinct, then ex and ey must be null, have a null intersection. And of course, if I take the union of those events over all elements in the support, I must get omega. To reiterate this procedure, the way to calculate the probability mass function for a random variable x is the following. First, enumerate all possible outcomes of the random experiment, and doing so, enumerate all possible values x of the random variable. Then, for each possible value x, find the event E sub x, those outcomes that give rise to the event that the random variable takes value little x. Add up those probabilities, consistent with the discrete probability law, to get the probability that the random variable takes that value. And now repeat for all possible values. Let's now discuss the simplest discrete random variable, the Bernoulli random variable. The Bernoulli random variable takes only two values. In other words, the outcomes, omega, are partitioned into two parts, each part assigned a distinct value under the Bernoulli random variable x. We will often, although it's not essential, call these two values 1 and 0. For example, in the case of a coin flip, we assign the value 1 to the outcome of the random experiment being a head, and the value 0 when the outcome is a tail. As written here, x is a 1 when omega is a head, x is a 0 when omega is a tail. Labeling 1 as a head and 0 as a tail is not essential. It could be the other way around. It could also be two other numbers. But it turns out, for most purposes, this is a useful definition. Then, the probability mass function for this random variable is obtained using the procedure given on the previous slide. In particular, P of 1 is the probability that we have the outcome of a head, which is, in this case, P, some number given to us giving the bias of the coin. Likewise, the probability of 0 is the probability that the coin is a tail, and that must take probability 1 minus p. So if I write x tilde ber p, that's to be read as x, the random variable, is distributed as, that's what tilde means, ber for Bernoulli with bias p. In other words, x is a Bernoulli random variable with bias p. We'll often speak of Bernoulli random variables as capturing this notion of a random biased coin flip. But really, the concept is ubiquitous and applies to any dichotomous situation. That is, Any situation that results in either success or failure, or more generally, any one of two outcomes. So here's some examples. Let's say that the random experiment is the state of a telephone at a given random time. The telephone can either be free or busy. We might let the Bernoulli random variable capture that situation, assigning the value 1 if it's free or 0 if it's busy. A person at any given time might be either healthy or sick with a certain disease. We will call a person who's healthy as the Bernoulli random variable 1, and the person who's sick, Bernoulli random variable 2, Bernoulli random variable 0, rather. Finally, the preference of a person who can either be for or against a certain political candidate. For could be mapped to 1, against could be mapped to 0. Next, let's talk about the binomial random variable. Let's again suppose that a coin with probability of heads p is tossed n times in a row, and each toss results in either heads or tails. I define the random variable x to be the number of heads that result from those n tosses. This is a basic concept in many real phenomena. I have a notion of a random trial that will result in either success or failure, and I repeat that trial n times. And what I care about is the number of successes in those n trials. That random number of successes is going to be a binomial random variable. And we say that that random variable x is binomial with parameters n, the number of trials, and p, the probability of success in each trial. And we'll write x tilde bin np to be read as the random variable x is distributed as a binomial random variable with parameter n and p, in particular n trials and success probability p. Now, what possible values can such a random variable take? It can take any value between 0 and n. And in particular, the event that x equals k corresponds to having k successes and necessarily n minus k failures. But there are multiple ways in which I can have these k successes. Think of the simple example when n equals 3 and k equals 2. That is, I have 3 trials and I'm interested in the probability of the event that I have 2 successes. Those 2 successes could come on the first 2, the last 2, or the first and third trials out of the 3. In general, what I'm asking for is the following. Given that I'm going to have n trials, 1 through n, I want to know how many ways can I select k of those trials for success. I'm selecting without regard to order, and therefore the number of ways for me to pick k trials to form the successes out of the n trials total is n choose k. That is, there are n choose k distinct length n binary sequences with k ones. In the example where I had n equals 3 and k equals 2, the 3 distinct binary sequences with 2 ones are 1, 1, 0, 1, 0, 1, and 0, 1, 1. Any such k sequence, that is, an n sequence with k successes, is equally likely as any other. That is, the probability that I have success on trials 1 and 2 is equal to the probability that I have success on trials 1 and 3, and equals to the success probability for trials 2 and 3. Therefore, it does not depend in what particular position I have my successes in my n trials. Any such sequence will have the same probability of success, namely p to the k times 1 minus p to the n minus k. Here, p to the k is the probability of success, and since I must have success on k trials, I must have p times p times p, k-fold, to get the probability of those k successes. But I also must have failures on n minus k of the trials. and each trial is a failure with probability 1 minus p. And therefore, the probability of n minus k failures is 1 minus p to the n minus k. Putting this all together, the binomial probability mass function has element pk, which stands for the probability that the binomial random variable x takes value k, meaning it has k successes out of n trials, is given by the following expression. N choose k, the number of ways to choose the k successes out of the n trials, p to the k, the probability of having those k successes, times 1 minus p to the n minus k, the probability of having those n minus k failures. And this k is defined for all k between 0 and n. So recall the binomial theorem. It says the following. Given any two real numbers, x and y, and any natural number n, the quantity x plus y to the power n is given by the sum over k from 0 to n of n choose k, x to the k, y to the n minus k. For example, in the case for n equals 2, this is the basic identity that x plus y squared is x squared plus 2xy plus y squared. The binomial theorem allows us to verify that the binomial distribution sums to 1. In particular, if I sum up p of k over all possible k, that is, I'm summing the probability of there being k successes out of n trials over all possible values of k from 0 to n, forming the support of the random variable, and I substitute in the expression for the probability mass function, and apply the binomial theorem, where in this case x equals p and y equals 1 minus p, then by the binomial theorem that equals p plus 1 minus p to the power n, which of course simply equals 1. Next, let's talk about the geometric random variable. We've actually met the geometric random variable before when we were talking about coin flips on the first homework. But let's reintroduce the concept now using the language of random variables. A coin with probability of heads p, given to us between 0 and 1, is tossed repeatedly until a head comes up. And we define the value of the random variable to be the number of coin tosses required. So if we think of the realization of the sequence of coin tosses as being encoded by a binary sequence, where 0 counts for tails and 1 counts for heads, then for example 001 encodes the idea that the first two tosses were tails and our first head came up on toss 3, and therefore the random variable x takes value 3. More generally, the event that x equals k, for k equal to some integer, corresponds to the outcome omega, where I'll have k minus 1 tails, or failures, or zeros, followed by 1 success, or head, or 1. I'll use the notation x sim GOP to be read as the random variable x is distributed as a geometric random variable with parameter p. And p here is the probability of success on each of the Bernoulli trials. Then the probability mass function for x has components p of k, where p of k, the probability that in a sequence of independent Bernoulli trials, each of which results in a head or success, probability p, the probability that that takes k trials to see the first success is 1 minus p to the k minus 1 times p, the probability that we have k minus 1 failures and our first success on trial k. Let's check that this is a valid probability mass function. First, as our tool, let's recall the expression for the summation of a geometric series. If a is strictly between 0 and 1, then if I form the geometric sum a to the 0 plus a to the 1 plus a squared plus a cubed, etc., that equals 1 over 1 minus a. With that in mind, let's look at summing up the components of the probability mass function for a geometric random variable. Substituting in the expression we just put in, developed in the last slide, 1 minus p to the k minus 1 times p, we see we can pull out the common factor p as it does not depend upon k. And now, if I think of 1 minus p as the quantity a, we see that what we're going to have is the sum 1 minus p to the k over all possible k. And that, using this formula, gives us 1. Before moving on to the Poisson random variable, let's stop for a minute and contrast these three distributions, the Bernoulli, the binomial, and the geometric. Underlying the binomial and the geometric is the basic notion of a Bernoulli random variable, a random trial with probability of success p that results in either success or failure. With the binomial distribution, I fix n, the number of trials, and the random variable is x, the number of successes in those n trials. With the geometric random variable, I'm again using the Bernoulli random variable as my basic component. But now, instead of specifying in advance the number of trials, I say I'm going to repeat that random experiment, that Bernoulli random variable, as many times as required until I get a success. And the outcome of the random experiment is simply the number of trials required. So keep that in mind so you don't confuse the Bernoulli, the binomial, and the geometric. Lastly, let's talk about the Poisson random variable. A Poisson random variable, x, has a parameter lambda and is denoted x is distributed as Poisson with parameter lambda. The definition of the Poisson random variable, probability mass function, is the following. P of k is e to the minus lambda times lambda to the power k over k factorial. And the support of the Poisson distribution is all non-negative integers, 0, 1, 2, up to infinity. And we assume that the parameter lambda is any non-negative real number. Let's recall the power series expansion of the exponential e to the x. E to the x is equal to 1 plus x squared over 2 factorial plus x to the cube over 3 factorial, etc. Using that, we can show that the Poisson random variable PMF is valid, that is, that it sums to 1. We sum from k equals 0 to infinity the components pk, given here, substitute in the form for p of k, identify that e to the minus lambda does not depend upon k and therefore can be pulled out. And now we see we have the sum from k equals 0 to infinity of lambda to the k over k factorial. Treating lambda as x in our power series expansion, we see we're going to be given e to the minus lambda times e to the lambda, which equals 1. It may not be clear the motivation for the Poisson random variable, but in fact it's useful in a wide variety of contexts. In particular, as we'll show here and on the next slide, the Poisson random variable is a good model for certain limits of binomial random variables when n grows large, and p, the probability of success, is in fact shrinking with the number of trials such that the product of the number of trials times the probability of success in a given trial converges as n grows large to a constant lambda. The computational benefit of this is that the binomial distribution, which requires calculation of binomial coefficients, which are expressed in turn in terms of factorials, can be computationally cumbersome. On the other hand, the Poisson approximation does not involve these coefficients and can be much simpler to compute. As an example, let's suppose we're doing 100 trials, where in each trial there's a success probability of 1%. Let's define the random variable x as binomial NP. So x is the number of successes in those 100 trials, each of which occurs with probability p equals 0.01. Let's also define the random variable y as a Poisson random variable with parameter lambda, where lambda is equal to the product n times p. In this case, n times p equals 1, so lambda equals 1. For example, for k equals 5, we can compute the probability mass function for x as 100 choose 5, 1 over 100 to the power 5, times 99 over 100 to the power 95. And you'll need a pretty good calculator and probably a computer to compute this to be 0.0029. On the other hand, we can compute the PMF for y, the Poisson random variable, at 5, to be e to the minus 1, recall that lambda is 1, 1 to the 5th, over 5 factorial, which equals 0.00306, fairly close to x. That concludes Lecture 2b for ECE 361. See you in class next week.